Hey everyone, and welcome. Today, we're diving into a hidden world that honestly determines the strength and safety of, well, almost everything, from jet engines to medical implants. It's called surface integrity. We're going to go on a journey to uncover the secret health report of the materials that build our modern world. So it all starts with this really critical question. We build these incredibly precise, high-tech components, right? So why do they sometimes fail, completely out of the blue? The answer, it turns out, isn't usually a flaw in the design itself. Nope, it's an invisible problem, hiding right there on the surface of the material. So here's our game plan. First, we're going to define what surface integrity even means. Then we'll start our investigation right on the surface, checking out its texture. After that, we'll dive deeper to uncover these hidden stresses and changes to the material's actual structure. And finally, we'll see how all these clues come together to give us the complete picture. Okay, so first up, what is surface integrity? The best way to think about it is like a complete health report for a material's surface. It details every single thing it went through during manufacturing. This goes so much further than just asking, hey, is it smooth? Surface integrity is the study of every single change a surface goes through when it's made. We're talking texture, hidden stresses, even microscopic damage. It's really the difference between a quick glance and a full-on diagnostic workup for a part that absolutely cannot fail. So our investigation kicks off at the most obvious layer, the surface texture. This is the part we can actually see and feel. But to really get what's going on, we need to measure it with some serious scientific precision. And the key metric here is something called RAW, which stands for arithmetic average roughness. The idea is actually pretty simple. If you imagine the surface as a microscopic mountain range, RAW is just the average height of all those little peaks and valleys. It boils all that complexity down to one powerful number that describes its texture. So, how do we actually measure this? Well, there are two main ways. The first one is the contact method. This works kind of like a tiny record player, where a diamond stylus physically traces the surface. Then you've got the non-contact methods. These are super cool. They use lasers or light to create a detailed 3D map without ever touching the material. It's absolutely perfect for delicate surfaces. But surface texture is only one piece of the puzzle. Now we've got to go deeper, into the invisible world of hidden stresses that are lurking just below that surface. These are called residual stresses. Okay, imagine the manufacturing process locking these tiny, powerful springs deep inside the material. Some of those springs are trying to pull the material apart. That's called tensile stress, and it's bad. Really bad, and helps cracks form. But other springs are trying to push the material together. That's compressive stress, and that's good. It holds the material tight and helps it fight off fatigue. Now, to find these invisible forces, engineers use a really cool technique called X-ray diffraction, or XRD. It literally shoots X-rays at the material, and by measuring how those X-rays bounce off the atomic structure, it can calculate the hidden strain and stress. It's a powerful, non-invasive way to see the unseen. And this brings us to a huge takeaway. Intentionally engineering these good compressive stresses, well, that's the whole secret to making parts last longer. It is absolutely fundamental for preventing fatigue and cracking in anything that's high performance. Another common technique is called the hole drilling method. This one's a bit more direct. You drill a very small, very precise hole, which relieves the stress right around it. The material literally relaxes, and by measuring that tiny little deformation with super sensitive strain gauges, you can work backward to figure out exactly what the stress was before you drilled the hole. Okay, so we've looked at the surface and the stresses just below it. Now we're going to examine the material's fundamental DNA, its hardness, and its microstructure. This tells us how the manufacturing process physically changed the material itself. And to do this, engineers have a whole toolkit of investigative instruments. Each one gives them a different clue about the story of what happened to that material during manufacturing. It's like a little detective kit. So first up is micro-hardness testing. This uses a tiny diamond to press into the surface, telling you how resistant it is to scratching. Next is the scanning electron microscope, or SEM, which gives you these unbelievable high magnification images. You can see tiny cracks, changes in the grain structure, everything. And finally, there's optical microscopy, which is often used on a cross-section of the part to see what's really happening below the surface. Now, these tools often turn up something really important, known as the white layer. Think of it like scar tissue on the metal. It's this super hardened and often brittle layer created by the intense heat of machining. Now, depending on what you're making, this layer can either be a benefit or a major red flag that failure is on its way. And that brings us to the number one goal in a lot of advanced manufacturing: controlling the thickness of this white layer. Because its presence, and especially its size, reveals so much about the quality of the machining process. Minimizing it is often absolutely critical for making sure a part is reliable. So we've looked at roughness, stress, hardness, and the microstructure. Let's put all of these pieces together now and see how they give us that complete picture of a surface's health. This right here, this is the entire toolkit summarized. As you can see, for each piece of the surface integrity puzzle, there's a specific tool for the job. We use profilometry for roughness, XRD for stress, and we use microscopy to analyze that microstructure and find the white layer. It's a really systematic approach to get a full diagnosis. And this is why it all matters. Having this complete picture isn't just some academic exercise. It lets engineers fine-tune their manufacturing. It lets them accurately predict how long a part will last in the real world. And most importantly, it lets them prevent the kind of catastrophic failures we talked about at the very beginning. It's all about safety, reliability, and pushing the boundaries of what we can build. So I'll leave you with this question. We've journeyed from the visible surface all the way down to the atomic structure. As our materials and our manufacturing get even more advanced, what new, hidden layers of integrity are we going to need to uncover to build the future? Thanks for joining me.